While Tyrannosaurus rex ruled the land, something nearly 17 meters long, about 56 feet, was hunting in the oceans. Tyrannosaurus rex never knew it was there, and that is not even the most extreme creature this ancient ocean produced. Long before the first dinosaur appeared, a predator hunted with self-sharpening bone blades instead of teeth. Its jaws could snap shut with enough force to crush armored prey. Later, an animal evolved something even stranger, a jaw made from a continuous spiral of teeth. Scientists discovered its fossils more than a century ago and spent decades arguing over how such a structure could possibly have worked. Then there were the giant marine reptiles. One found in Arctic rock had a snout filled with dense networks of blood vessels, suggesting it could detect prey with a sensitivity unlike almost anything alive today. And while dinosaurs were walking along the shores of the ancient oceans, another predator was hunting beneath them with a reinforced skull built to strike prey hard enough to leave evidence in its own fossilized stomach contents. All of these animals were real, all of them left fossils behind, and none of them were dinosaurs. The ocean had been experimenting with predators for hundreds of millions of years before the great reptiles dominated the land, and it kept producing body designs that gravity would never have allowed on shore. Tonight, we're going back into those ancient oceans to uncover the predators that ruled beneath the surface, the strange weapons evolution gave them, and why the sea repeatedly produced hunters that could rival anything walking on land. But before we continue, if you're enjoying these journeys into the stranger side of Earth's history, consider giving the video a like and subscribing. And tell me in the comments which prehistoric creature has always fascinated you the most. Let's sink beneath the ancient seas and meet the predators waiting there. The creatures ahead of us belong to worlds that vanished long before anything resembling human history. They were not dinosaurs, even when they occupied the same broad stretches of geological time. Mosasaurs were squamate reptiles, related to the lineage that includes modern lizards and snakes. Pliosaurs and other plesiosaurs followed a separate branch of marine reptiles. Ichthyosaurs evolved from land-dwelling reptiles along their own path, while placoderms belonged to an ancient lineage of armored fishes. Their bodies may have solved familiar problems, finding prey, pursuing it, and taking it into the jaws. But evolution arrived at those solutions independently, again and again. That distinction becomes important once the scale of the story comes into view. The ocean offered something the land could not. Water carried much of an animal's weight, allowing buoyancy to support enormous bodies, while muscles and skeletons were freed for other demands. An aquatic predator could devote more of its architecture to jaws, sensory organs, propulsion, and the control of a massive body moving through 3 dimensions. On land, every kilogram had to be supported against gravity. In the sea, the surrounding water became part of the animal's mechanical environment. Across hundreds of millions of years, this difference repeatedly shaped the upper limits of predation. The largest hunters were not variations on a single design. Some carried armor like living fortresses. Others developed extraordinary teeth, immense skulls, flexible jaws, or sensory systems capable of reading disturbances beyond immediate sight. Their forms changed with the seas around them, yet the same physical opportunity remained available, allowing natural selection to explore sizes and structures that terrestrial predators could rarely approach. The span itself is difficult to hold in the mind. The first creature we will meet lived about 375 million years ago, during the Devonian. The last of these great marine predators disappeared about 66 million years ago at the end of the Cretaceous. Between those points lie more than 300 million years of changing continents, shifting coastlines, rising mountains, disappearing seas, and mass extinctions that repeatedly cleared entire branches from the tree of life. Tyrannosaurus rex lived near the end of that interval, meaning it was separated from us by less time than separated it from the armored predator waiting at the beginning of this story. We know these animals through fragments that survived those immense intervals. A mineralized bone can preserve the proportions of a skull. An armored plate can reveal where muscles once attached. A tooth embedded in another animal's bone can record an ancient attack. Stomach contents can preserve the remains of a final meal, while microscopic traces inside fossilized structures can reveal details invisible from the outside. Modern computed tomography can pass through stone without damaging the specimen, exposing internal anatomy that earlier generations could only imagine. Biomechanical models can then test how those structures may have moved, bitten, accelerated, or turned. The result is not a complete portrait. It is something more delicate, assembled from evidence scattered across ancient rock. The continents these animals inhabited were arranged differently, and many of their seas were warmer than those of today. Shorelines crossed places that are now deserts, plains, cliffs, and mountains. Beneath those landscapes remain pieces of vanished ecosystems, preserved by burial, mineralization, and extraordinary geological chance. From that scattered evidence, a sequence begins to emerge. The first creature belongs to a time 130 million years before the earliest dinosaurs, carrying a jaw unlike anything the later reptiles would ever possess. Its story begins in the Devonian seas, where armor and bone became instruments of predation on an immense scale. Before the first great dinosaurs appeared, an armored fish had already turned its mouth into a cutting machine. Dunkleosteus terrelli lived during the late Devonian, roughly 375 to 358 million years ago, when much of the world was covered by broad continental seas. Its remains have been recovered from places now separated by oceans, including northern Ohio, Belgium, Morocco, and Poland, suggesting that this was not an isolated curiosity, but a predator with a remarkably broad reach. What remains of Dunkleosteus is mostly its head. The rear portion of the animal was built from tissues that rarely survive burial, while the skull and forward body were protected by thick bony plates. Those plates locked together across the head and chest, forming a rigid shield that could withstand the struggles of large prey. Estimates of the full animal vary from about 3.5 meters, nearly 12 feet, to about 6 meters, roughly 20 feet, because the missing rear body leaves scientists reconstructing much of its length from the parts that endured. That uncertainty makes the preserved armor even more revealing. The plates were not passive protection, they shaped the entire architecture of the animal, providing anchor points for powerful muscles and creating a head built around force. Yet the most unusual part was hidden in plain sight at the front. Dunkleosteus had no teeth. Instead, the edges of its jaw plates extended into sharp, exposed blades. Upper and lower plates met during a bite, sliding against one another in a way that continually honed their cutting surfaces. The action resembled a pair of blades maintaining their edge through contact, except these cutting tools were living bone, permanently attached to the skull. There was no separate tooth to fall out, wear down, or wait to be replaced. Each bite helped preserve the weapon used by the next one. The arrangement was especially useful in a Devonian ocean filled with other armored fishes. Placoderms carried protective plates over much of their bodies, creating prey that could be difficult for ordinary jaws to penetrate. Dunkleosteus possessed a cutting system capable of meeting armor with armor, concentrating force along narrow edges until the protective surfaces gave way. The result was a predator whose defenses and feeding apparatus belong to the same integrated structure. Even its name carries a trace of the people who recovered this vanished world. The genus honors David Dunkel, a paleontologist associated with the study of the Cleveland Shale fossils, while the species name Torelli recognizes J. Terrell, whose specimens helped bring the animal to scientific attention. The fossil itself had already spent hundreds of millions of years waiting in stone before anyone could give those plates a name. There are also traces of what happened after Dunkleosteus became large enough to dominate its surroundings. Some fossilized bones of Dunkleosteus bear wounds whose spacing and geometry correspond to the animal's own jaw blades. Such marks point toward attacks between members of the same species, with larger individuals capable of turning the same formidable apparatus against smaller ones. Cannibalism was not an abstract possibility preserved in anatomy alone. The evidence is written directly into damaged bone. For approximately 24 million years, Dunkleosteus remained part of the uppermost tier of Devonian marine ecosystems. That interval stretches across a period longer than the time separating modern humanity from the extinction of the non-avian dinosaurs. During all those ages, generations of this armored fish carried the same basic solution in their skulls, a jaw that did not need to grow a new weapon because the weapon sharpened itself through use. The animal's strangest achievement was therefore not simply possessing enormous jaws. It was making the act of feeding part of the mechanism that maintained them. The most revealing part of Dunkleosteus was not the edge of its jaw, but what happened in the instant before those edges met. In 2007, biomechanists Philip Anderson and Mark Westneat examined the mechanics preserved in its armored skull and found that the animal could turn the opening of its mouth into a rapid movement of water. Ordinary jaws open by rotating around a hinge, with the lower jaw dropping away from the skull. Dunkleosteus had an additional mechanical advantage. Its craniothoracic joint, the connection between the armored head and the body, allowed the head plates themselves to move upward as the mouth opened. The result was a gape that could expand with unusual speed, enlarging the space inside the mouth in a fraction of a second. Water responds immediately to that change in volume. As the oral cavity expanded, surrounding water rushed inward, carrying suspended material toward the opening. This created a suction feeding event, not merely a bite. A small fish caught within the flow could be drawn closer before its muscles had enough time to produce an effective escape movement. The distance between predator and prey could disappear through physics alone. Then the jaws closed. The same structure that opened rapidly could snap shut with remarkable force. For a specimen reconstructed at about 6 meters, roughly 20 feet, estimates have placed the pressure at the cutting edges near 55,000 kilopascals, about 8,000 pounds per square inch. That figure is an estimate rather than a direct measurement, but it illustrates the mechanical scale involved. The pressure was concentrated along narrow, bony blades, turning the closing motion into a shearing action capable of penetrating heavily armored prey. The feeding sequence therefore worked as a chain of connected events. The head rose, the mouth expanded, water accelerated inward, prey was carried toward the jaws. Then the plates converged, and their sharpened edges met with concentrated force. Nothing depended on a separate tooth remaining intact. The cutting surfaces were part of the skull itself, and their contact during feeding helped maintain their sharpness. This arrangement also changed the relationship between speed and strength. A massive predator does not necessarily need to chase every meal across open water if its mouth can alter the surrounding flow quickly enough to bring prey within reach. Dunkleosteus could combine the sudden movement of suction feeding with the crushing and slicing power of its armored jaws. Each part supported the next, producing a feeding system in which acceleration, water movement, and mechanical force were closely linked. The fossil record cannot preserve the rush of water around an ancient skull, but bone geometry preserves the architecture that made such movement possible. Computer models can reconstruct the positions of the jaws, estimate muscle forces, and calculate how rapidly the mouth could expand. Those reconstructions turn a collection of mineralized plates into a mechanical system that can be tested against the laws of motion. For millions of years, that system remained successful in Devonian seas. It was not simply a powerful bite attached to an armored animal. It was a coordinated mechanism that used the surrounding water as part of the attack, drawing prey inward before the final closure of the jaws. The ocean itself became involved in the moment of feeding, and the boundary between predator, weapon, and environment became remarkably thin. The importance of that mechanism becomes clearer when its pieces are considered together. A jaw that merely closes with force is one thing. A jaw that first changes the flow of water, brings material inward, and then concentrates its own closing force along self-maintaining blades is something more integrated. Dunkleosteus had effectively made the first stage of feeding part of the weapon itself, allowing the surrounding water to participate before the bone plates completed the motion. For more than a century, Helicoprion was known almost entirely by a single object, a spiral of teeth that seemed to belong to an animal assembled from unfamiliar parts. The fossil had been recovered in the Ural Mountains in 1899 by Russian geologist Alexander Karpinsky, and from that beginning, a long scientific puzzle took shape. The creature itself lived during the Permian, between about 299 and 252 million years ago. Helicoprion was a cartilaginous fish, related more closely to modern ratfish and chimeras than to sharks. Its body was probably between about 4 and 7 meters, roughly 13 to 23 feet, long, although the fossil record makes precise reconstruction difficult. Cartilage usually disappears during burial, leaving little behind. In Helicoprion's case, however, the teeth were mineralized strongly enough to survive, preserving the most distinctive part of its feeding apparatus, while almost everything around it vanished. What survived was a tooth whorl, a tightly coiled structure in which individual teeth were joined together at their bases. New teeth developed along the outer portion of the spiral and pushed older teeth inward, creating a continuously renewing sequence. The largest known whorls reached nearly 90 centimeters, about 35 inches, across. Seen by itself, the structure resembles a natural spiral carved from stone, but each turn contains evidence of repeated tooth replacement and growth. The arrangement created a problem that lasted for generations. Without a skull, scientists could not determine where the spiral belonged. Early reconstructions placed it at the front of the upper jaw, where it would have projected outward like a curved blade. Other interpretations moved it to the lower jaw. Some placed it at the tip of the snout, while still others imagined an entirely different position on the body. Each proposal tried to make the fossil fit an animal whose missing anatomy could no longer correct the guess. The uncertainty persisted because the whorl itself was so unusual, preserving its own history of growth while withholding the anatomy that would explain its position. A conventional tooth row gives paleontologists clues through its relationship to surrounding bone, but Helicoprion offered almost no such context. There was no complete skull to reveal a hinge, no preserved jaw arch to define the opening of the mouth, and no intact skeleton to show how the strange coil connected to the rest of the animal. Fragments appeared across widely separated parts of the ancient world. Whorls have been discovered in the former Russian territories of the Ural region in Western Australia, Norway, and Idaho, showing that Helicoprion was distributed across broad marine environments. Yet geographic abundance did not solve the anatomical mystery. Each specimen carried the same remarkable spiral, while the rest of the animal remained largely absent. The fossil, therefore, became more than a tooth structure. It became a reminder of how easily a vanished animal can be reduced to one durable part. Generations of paleontologists could study the spiral in extraordinary detail while still lacking the anatomy needed to place it correctly. The animal existed in the evidence, but only in fragments, and every reconstruction depended on interpreting what the rock had preserved against everything it had allowed to disappear. By the early 21st century, the whorl had been studied for more than 100 years, yet its position inside the mouth remained unresolved. The mystery endured not because the fossil was too poorly preserved to examine, but because the surviving structure was so complete and so unfamiliar that its true relationship to the missing skull could not be read from the surface alone. The answer had been sitting inside the fossil all along, hidden beneath layers of mineral and stone. In 2013, paleontologist Leif Tapanila of Idaho State University and his colleagues turned to computed tomography, using detailed imaging to examine a Helicoprion specimen that had been collected in Idaho in 1950. It had spent decades in a museum collection, preserving structures that could not be seen from its exterior. The scan revealed something far more complete than the researchers had expected. Within the fossil, the tooth whorl could be traced through the lower jaw, showing that the spiral was not an external ornament or a blade projecting from the snout. It occupied the mandibular arch itself, extending through the lower jaw and supported along its central line. The strange coil was therefore not attached to the mouth. It was part of the mouth. That placement changed the animal's entire appearance. Earlier reconstructions had imagined Helicoprion carrying its spiral visibly at the front of the face, producing a creature whose anatomy seemed almost impossible to reconcile with ordinary feeding. The internal position offered a much more coherent arrangement. The teeth could remain within the boundaries of the lower jaw while still moving as the mouth opened and closed. The discovery also settled another long-standing uncertainty. Helicoprion was not a shark. Its evolutionary position belonged among the stem holocephalans, an ancient branch more closely related to modern chimeras and ratfish. The resemblance to sharks had come largely from its general fish-like form and its position within the broader group of cartilaginous fishes. Beneath that resemblance was a different lineage, following its own evolutionary path. The mechanics of the spiral were equally unusual. As Helicoprion closed its mouth, the whorl could rotate within the lower jaw, bringing successive teeth into contact with prey. Rather than simply clamping down and holding, the motion appears to have drawn material inward while the teeth cut through it. The action has often been compared to a circular saw, though the living mechanism was more intricate, with the rotation and growth of the tooth row working together as one continuous system. That arrangement may also explain why such an elaborate structure evolved in the first place. Helicoprion probably did not depend on crushing thick shells or breaking large bones. Its teeth were better suited to cutting and drawing prey inward. Soft-bodied cephalopods, including ammonites, nautiloids, and other relatives of modern squid, have been proposed as likely targets. Such animals could be difficult to hold with an ordinary bite, especially when their bodies were flexible and their shells offered limited purchase. A rotating tooth whorl could instead begin cutting at the front and progressively pull the prey deeper into the mouth. The fossil does not preserve the movement itself, but the arrangement of the teeth provides a record of repeated growth. New teeth formed toward the outside of the whorl, while older teeth were carried inward. The spiral therefore recorded successive stages of the animal's feeding apparatus, almost like a biological archive preserved in mineral. Helicoprion endured for approximately 45 million years, crossing changing marine environments and surviving shifts in ocean chemistry that altered the communities around it. During that immense span, its peculiar jaw remained recognizable, a specialized solution carried through generations of an ancient lineage. Eventually, the Permian world approached its greatest biological crisis. At the boundary between the Permian and Triassic periods, marine ecosystems would undergo a transformation on a scale unlike anything Helicoprion had previously encountered. The spiral that had endured for millions of years would disappear with the world that had sustained it, leaving behind only the coiled record of how strangely evolution had once learned to feed. Along the Somerset coast, a fragment of ancient bone emerged from the rock, carrying an outline far larger than anyone expected from a creature of the Triassic. It belonged to Ichthyotitan severnensis, an ichthyosaur that lived near the end of the period, when these air-breathing marine reptiles had already spent more than 150 million years adapting their bodies to life at sea. Ichthyosaurs were not fish, although their streamlined forms could resemble them at a glance. They breathed air, carried lungs, and descended from terrestrial reptiles that had returned to the water. Through convergent evolution, their bodies acquired features suited to fast movement through an open ocean, including powerful tails, compact flippers, and streamlined trunks. Some eventually reached dimensions that placed them among the largest animals ever known from the fossil record. The first clue to Ichthyotitan was a piece of jawbone so substantial that its finder initially identified it as belonging to a dinosaur. The mistake made sense within the landscape, where enormous fossil bones can be difficult to place when only a fragment survives. The specimen was eventually recognized as belonging to an ichthyosaur, but the scale of the animal remained uncertain until more evidence appeared. In 2020, 11-year-old fossil collector Ruby Reynolds and her father, Justin, discovered additional jaw material eroding from a coastal cliff in Somerset, England. The new pieces belonged with the earlier fragment, allowing researchers to compare their proportions and recognize a previously unknown species. Paleontologist Dean Lomax and his colleagues formally described Ichthyotitan severnensis in 2024, estimating a total length of about 25 meters, roughly 82 feet. The estimate rests on the dimensions of the jaw and comparisons with better-known ichthyosaurs. It is not the same as possessing a complete skeleton, because no complete body of Ichthyotitan has been recovered. Yet the surviving bones preserve an extraordinary scale. The jaws alone may have reached about 2 meters, roughly 6.5 feet, in length, creating an opening large enough to encompass animals that would themselves have been substantial predators. Ichthyotitan lived approximately 202 million years ago, near the end of the Triassic. On land, the earliest dinosaurs were spreading into ecosystems that would eventually become theirs to dominate. In the sea, another lineage had reached a very different extreme. The two worlds were developing their great predators on separate evolutionary paths, with no need for either to resemble the other. Its feeding behavior must be reconstructed from related ichthyosaurs, since no preserved hunt can tell us exactly how Ichthyotitan moved through the water. The most plausible interpretation is pursuit predation. A large ichthyosaur could use its streamlined body and powerful tail to maintain speed while closing on sizable prey, then bring its enormous jaws forward with a broad gape. Other marine reptiles occupied the same seas, providing potential targets for a predator whose mouth had evolved on such an immense scale. The proportions suggest an animal built for more than simply carrying great mass. Its body was shaped around movement, breathing, and repeated pursuit, while the jaws provided the final means of securing prey. The enormous size was therefore part of an integrated aquatic design, not merely an enlarged version of a smaller reptile. For Ichthyotitan, the fossil record preserves only fragments of that life, pieces of jaw emerging from stone along a modern coastline. Yet, those fragments are enough to reveal a marine reptile whose dimensions approached the upper limits of what evolution had produced in the ocean by the close of the Triassic. The shape of a pliosaur began with an absence, where its long-necked relatives carried a graceful chain of vertebrae between body and skull. The pliosaur reduced that connection until the head seemed almost to grow directly from the torso. This shifted the animal's mass toward the front, creating room for enormous jaw muscles and a skull built around predation. Pliosaurs belonged to the plesiosaur lineage, but their bodies followed a different path from the long-necked forms that shared their seas. The neck became short and powerful, while the head expanded into one of the dominant features of the animal. Their bodies remained compact, with four broad flippers extending from the sides. Each pair could contribute to movement differently, allowing these reptiles to adjust their position through the water with remarkable control. The front flippers could provide lift and help direct the body, while the rear pair contributed strongly to propulsion. Rather than relying on a single tail as the main engine, pliosaurs moved with four separate underwater surfaces. Their limbs could work together or alter their strokes, giving the animal control over changes in depth, orientation, and direction. In three-dimensional water, that versatility mattered. A predator did not need to follow prey along a single horizontal path. This body plan appeared across a remarkably broad span of geological time. Pliosaur fossils have been recovered from Africa, Australia, Asia, Europe, North America, and South America, showing that their lineage occupied marine environments across much of the ancient world. Their success was not confined to one coastline or climate. Different species adapted to changing seas while retaining the same fundamental arrangement of compact body, powerful head, and four flippers. The lineage emerged by the late Triassic and persisted into the Cretaceous, giving pliosaurs a long presence among the major marine predators of the Mesozoic. During that interval, other hunters appeared and disappeared, coastlines shifted, and marine communities changed. Pliosaurs repeatedly returned in new forms, their anatomy remaining recognizable even as individual species evolved toward different sizes and proportions. Their greatest evolutionary pressure may have come from within their own group. Fossil evidence records injuries consistent with attacks between large marine reptiles, including wounds attributed to other pliosaurs. Such encounters suggest that large hunters lived alongside other large hunters, creating competition over prey and space. A stronger jaw could secure larger meals. A more powerful body could control movement during an encounter. Selection could therefore push the same basic body plan toward increasingly formidable proportions. That competition unfolded within an environment where movement had no fixed surface beneath it. A pliosaur could rise beneath prey, descend into deeper water, roll its body, or alter its heading without first turning across solid ground. Its four flippers provided multiple points of control, allowing the animal to combine forward thrust with changes in pitch and rotation. Fish and sharks could achieve remarkable agility through tails and fins, but the pliosaur solution placed much of its maneuvering power in four large limbs. Over time, the skull became the defining expression of that design. Some species carried heads occupying an extraordinary share of their total body length, supported by compact necks and massive bodies. The result was a predator whose anatomy concentrated almost every major investment around locating prey, reaching it, and bringing an enormous set of jaws into position. Pliosaurs were not simply large reptiles that happened to live in the sea. Their bodies represented a distinct experiment in aquatic predation, combining four limb-driven movement with concentrated head mass and immense feeding structures. For millions of years, that experiment remained successful across changing oceans, leaving fossils that preserve the outlines of a lineage shaped by hunting in three dimensions. The name Kronosaurus carries an old mythology into the fossil record. It was chosen for Kronos, the leader of the Titans in Greek tradition, a figure associated with a generation that ruled before the Olympian gods. The name suited a pliosaur whose skull would become one of the most imposing structures known from the Cretaceous seas. Its first recognized remains came from Queensland, Australia, in 1899, when Andrew Crombie recovered six large conical teeth and donated them to the Queensland Museum. A quarter of a century later, in 1924, paleontologist Heber Longman formally described the animal. What began as a handful of teeth gradually became the outline of a predator built around an extraordinary head. Modern estimates place Kronosaurus at roughly 9 to 11 meters, about 30 to 36 feet in length. The skull occupied close to one-third of that body, giving the animal a head that may have approached 3 meters, nearly 10 feet, from its snout to the rear of the skull. In proportion to the body, this was not simply a large head. It was the center of the animal's design. The teeth followed the same principle. The largest reached about 30 centimeters, approximately 12 inches, from root to crown. They were smooth and conical rather than finely serrated, shaped for penetration and grip. A serrated tooth can slice through tissue as an animal pulls away, but a strong cone can enter deeply and remain anchored while immense forces pass through the jaw. Kronosaurus carried both the architecture of a clamp and the mass needed to make that clamp formidable. Fossilized prey preserves traces of how those teeth were used. Large round punctures and wounds appear in the bones of other marine reptiles, with spacing that can correspond to the tooth arrangement of Kronosaurus. Such marks provide more than an impression of feeding style. They preserve moments when one animal's anatomy met another's body, leaving a pattern in bone that remained long after the encounter itself had disappeared. The snout held another unusual feature. Internal chambers within the skull may have altered how vibrations and pressure were transmitted through the animal's head, potentially contributing to directional sensing in water. Researchers have proposed that this arrangement could have helped Kronosaurus identify the direction of chemical or pressure cues associated with prey. The precise function remains debated, but the anatomy suggests that the enormous skull was not devoted solely to biting. It also contained systems for gathering information from its surroundings. Kronosaurus inhabited the Eromanga Sea, a broad inland waterway that covered much of what is now western Queensland during the Cretaceous. The sea was warm and relatively shallow, supporting turtles, plesiosaurs, fish, and other marine reptiles. Within that environment, a predator carrying a head several meters long did not need to search an empty ocean. Its hunting ground contained a dense community of potential prey, each occupying different depths and habitats. Its dark dorsal surface and lighter underside may have provided countershading, reducing the contrast between the animal and the changing light above and below. From beneath, the paler underside could blend with the brighter water near the surface, while the darker back merged with deeper surroundings when viewed from above. This pattern appears repeatedly among modern marine predators, suggesting that concealment remained useful even across very different evolutionary histories. Kronosaurus was therefore shaped around more than raw size. Its skull concentrated muscle, teeth, sensory structures, and feeding mechanics into a single front-heavy design. The result was a predator whose anatomy left unusually direct traces in the fossils of the animals that shared its sea. Some fossils preserve the meal itself, leaving no need to reconstruct the diet from teeth alone. Within the body cavities of certain Kronosaurus specimens from northern Queensland, the remains of animals once swallowed have remained enclosed in stone. These fragments provide a rare kind of evidence, a record created not by interpretation but by the final contents of a predator's digestive system. Among the identified prey are sea turtles and elasmosaurid plesiosaurs, long-necked marine reptiles that could themselves reach substantial sizes. Their presence inside Kronosaurus shows that its feeding range extended well beyond smaller fish. The animal was capable of taking prey whose bodies occupied much of the same underwater world, including other large reptiles moving through the shallow Cretaceous seas. One fossil preserves an especially unusual trace of such an encounter. The skull of Aeromangosaurus, a long-necked plesiosaur, carries large rounded bite marks whose spacing corresponds closely with the teeth of Kronosaurus. The rest of the animal has never been recovered. Only the skull remained, suggesting that the body was separated from it during feeding or later dispersed after the attack. The bone records the geometry of the bite, while the absence of the remaining skeleton hints at what happened beyond the preserved fragment. Other injuries reveal that Kronosaurus did not always direct its jaws toward prey from another species. A juvenile Kronosaurus skull bears marks consistent with attacks by another large individual, indicating aggression within the species itself. Such wounds offer a glimpse into encounters that left no behavioral record, showing that the enormous jaws could also be turned against members of the same lineage. Then there is the fossil of an individual whose last meal may have become its final obstacle. One specimen, catalogued by the Queensland Museum, contains evidence of a swallowed sea turtle. The arrangement of the remains has been interpreted as consistent with choking during feeding. The possibility carries an unusual symmetry. A predator adapted to overpower large animals could still encounter a physical limit imposed by the size and shape of its own prey. Stones found within the abdominal regions of some pliosaur fossils add another layer to the picture. These gastroliths may have helped with digestion, although their precise function remains uncertain. They may also have contributed to ballast, helping an animal regulate its position in the water. Modern crocodilians swallow stones as well, but similar behavior does not prove that ancient pliosaurs used them in exactly the same way. The fossils simply preserve the presence of these stones within the body, leaving their role open to interpretation. Taken together, the evidence gives Kronosaurus a more detailed place within its ecosystem. Its teeth reveal the mechanics of capture, while the bones inside its body reveal the animals that actually entered its mouth. Sea turtles, long-necked plesiosaurs, and members of its own species all appear within the fossil record, each preserving a different part of the animal's life. Even the incomplete remains carry information. A damaged skull can preserve the spacing of a bite. A cluster of stones can remain where a digestive system once held them. A mass of turtle bones can survive inside a body cavity long after the surrounding flesh has disappeared. These traces transform the fossil from a shape into a record of behavior, allowing an extinct predator to be understood through the physical remains of the lives it intersected with. The most valuable evidence is often the least complete. A single preserved fragment can connect predator and prey across millions of years, while several fragments together can reveal the structure of an entire encounter. In this way, Kronosaurus survives not only as a skull and a set of teeth, but through the remains of the animals that once disappeared into it. Beneath the frozen ground of Svalbard, the first clues to Predator X emerged from stone that had preserved an ocean long gone. In 2006, a Norwegian paleontological expedition began excavating two enormous pliosaur skeletons from the islands, which lie far north of mainland Norway. The bones did not fit comfortably within any species then known. Their front paddles were unusually long, their vertebrae differed in shape, and the spacing of their teeth suggested an animal with a distinctive way of using its enormous skull. The incomplete picture soon acquired a name before it acquired a scientific identity. Newspapers called the animal Predator X, and early estimates placed it at roughly 15 meters, about 49 feet, in length, with a mass approaching 41 metric tons, about 45 tons, and an exceptionally powerful bite. Some reports proposed a force equivalent to roughly 231 million pascals, about 33,000 pounds per square inch, while the largest teeth were described as reaching about 30 centimeters, about 12 inches, from base to crown. Those early numbers carried a mixture of fossil evidence, reconstruction, and speculation, and the animal would spend years being separated from the mythology created around it. Behind the headlines, preparation moved at a much slower pace. The fossils had to be freed from their surrounding rock, examined bone by bone, and compared with other pliosaurs before a formal scientific description could be made. 6 years after the expedition began, the animal received its official name, Pliosaurus funki, in a study published in 2012 in the Norwegian Journal of Geology. It became only the fourth species of Pliosaurus formally recognized by science, placing Predator X within a lineage whose members had already occupied the Jurassic seas for millions of years. Later assessments brought its estimated length closer to 12 meters, about 40 feet, still leaving it among the largest marine predators known from the fossil record. Its skull alone reached roughly 2 meters, about 6.5 feet, a structure large enough to dominate the front of its entire body. Paleontologist Patrick Druckenmiller, one of the scientists who studied the animal, emphasized the exceptional size of its teeth, comparing their presence to something that could make a Tyrannosaurus rex seem modest by comparison. Pliosaurus funke lived between 147 and 150 million years ago, during the late Jurassic, when the northern seas supported an intricate community of marine reptiles and fish. Ichthyosaurs moved through the same waters with streamlined bodies. Long-necked plesiosaurs occupied other feeding roles, while early sharks shared the broader marine ecosystem. A fully grown Pliosaurus funke stood at the uppermost level of this food web, its body combining enormous flippers with a skull built for capturing substantial prey. Yet the fossils suggest that its significance was not simply a matter of becoming larger. The unusual proportions preserved in its skeleton point toward an animal shaped by a particular evolutionary history, one in which swimming, sensing, and feeding had to work together across a body measured in meters. Each vertebra, paddle, and tooth became part of a single aquatic design, preserved imperfectly but well enough to distinguish this predator from its relatives. Even the surrounding rock mattered, because the frozen Arctic setting protected portions of a marine ecosystem that would otherwise have been scattered and erased by time. For years, the story of Predator X centered on its dimensions and its jaws. Then, a later examination of its biology revealed another feature, one that reached beyond the obvious architecture of the skull and into the way this giant experienced the ocean around it. The most revealing part of Predator X was not the size of its skull, but the fine architecture hidden inside its surface. In early 2024, a British Broadcasting Corporation documentary presented by Sir David Attenborough examined an exceptionally preserved pliosaur skull from the Jurassic rocks of Dorset, England. Its completeness allowed scientists to study features that usually disappear long before a fossil reaches human hands. Computed tomography revealed an intricate network of channels running through the snout, carrying blood vessels and nerves toward the outer surface. The density of these passages was strikingly high, suggesting that the snout was doing more than supporting teeth and shaping the front of the skull. The arrangement pointed toward a sensory system capable of registering subtle changes in the surrounding water. Pressure disturbances created by moving animals could have traveled through the water and reached the sensitive tissues along the snout, while chemical gradients may have supplied additional information about the presence and direction of nearby prey. Such a system would have given Pliosaurus an unusual relationship with distance. Vision works best when something lies within a clear line of sight, but a pressure or chemical signal can spread through water before an animal itself becomes visible. A large pliosaur moving through the Jurassic Sea could therefore gather information from its surroundings without constantly relying on its eyes. The snout became part of the hunting apparatus, not because it struck first, but because it allowed the predator to interpret disturbances arriving from elsewhere in the water. Its mouth carried another layer of specialization. Pliosaurus possessed approximately 130 interlocking teeth, each reinforced by serrated edges, suited to penetrating and gripping flesh. These teeth were arranged through both jaws, creating a dense field of cutting surfaces that could hold struggling prey once contact was made. Estimates place the bite force at about 33,000 newtons, roughly equivalent to twice the estimated bite force of a large saltwater crocodile. The number is not merely a measure of strength. It represents the mechanical result of an enormous skull, powerful jaw muscles, and bones shaped to withstand forces generated during feeding. Then the four flippers added another dimension. Unlike a fish that depends mainly on a tail to generate forward motion, a pliosaur could coordinate its paired limbs to control movement through 3 dimensions. Biomechanical models suggest that Predator X could reach approximately 3 meters per second, about 10 feet per second, during a short burst. That acceleration would have allowed it to close the final distance rapidly, transforming sensory information into physical contact before many potential prey animals could create enough separation. Taken together, these features describe a hunting system built from several independent advantages. The snout could gather information from water moving around the animal. The flippers could redirect the body and produce a sudden approach. The jaws could then deliver enormous force through teeth shaped to penetrate and retain their grip. Each stage supported the next, reducing the distance between detecting prey and controlling it. What makes the fossil record especially interesting is that none of these abilities required a single extraordinary structure. They emerged from many smaller anatomical changes working together, preserved in bone and revealed through modern imaging and mechanical study. Predator X was therefore not simply a giant pliosaur with an oversized mouth. Its skull, senses, and swimming apparatus formed an integrated system for finding, reaching, and securing prey in a world where the water itself carried information. For millions of years, That combination occupied the highest levels of the Jurassic marine food web. Yet, evolution rarely preserves one solution forever. As the Jurassic seas changed and new marine reptiles expanded into the same ecological spaces, another lineage was already developing a very different way to dominate the water. The first mosasaurs did not arrive in the sea looking like monsters. They began as squamate reptiles, relatives of the lizards and snakes living on land, and then gradually transformed their bodies for life among the waves. By roughly 98 million years ago, this experiment had already produced marine hunters, and within a few tens of millions of years, their descendants had spread into an extraordinary range of forms. Some inhabited shallow coastal waters, while others became open ocean predators, filling ecological roles that had once belonged to very different reptiles. Their bodies reveal how completely that transformation took place. The limbs became broad paddles, useful for steering and adjusting position, while the tail developed into the principal engine of movement. Flattened from side to side and strengthened by powerful muscles, it could drive the animal forward in rapid bursts, while the flexible body followed behind. This gave mosasaurs an eel-like quality in the water, combining acceleration with the ability to bend through tight turns. Unlike fish, mosasaurs retained the basic skeletal inheritance of reptiles, yet reshaped it through countless generations until limbs, spine, muscles, and tail worked together as one fluid swimming system. Their swimming style was not simply an imitation of fish, it was a separate solution assembled from the anatomy of a land-dwelling reptile. The most remarkable adaptation appeared where feeding began. A mosasaur's skull could open far beyond the proportions suggested by its exterior shape because the lower jaws were divided into flexible sections. Instead of relying on a single rigid connection at the rear, each side incorporated another joint along its length. This double-hinged arrangement allowed the jaws to spread apart and accommodate prey wider than the front of the skull might imply. The result was a mouth capable of accepting large animals while maintaining enough flexibility to manipulate them after capture. Inside that opening was another set of teeth hidden along the roof of the mouth. These pterygoid teeth pointed inward and backward, forming a second gripping surface behind the main row. Once prey entered the mouth, those teeth could hold it while the jaws shifted their position. The arrangement worked almost like a biological ratchet. One part of the mouth maintained contact while another advanced, allowing the animal to draw substantial prey deeper without relying on a single crushing bite. Such anatomy became increasingly useful as mosasaurs diversified. Their fossils now occur on every continent, including Antarctica, showing that these reptiles had reached an enormous geographic range before the end of the Cretaceous. Their remains appear in deposits representing shallow seas, continental shelves, and more open marine settings, reflecting a lineage that had become deeply integrated into the world's changing oceans. Reproduction brought another remarkable departure from the older marine reptile pattern. Fossil evidence preserving developing embryos within mosasaur remains indicates that at least some species gave birth in water rather than returning to land. Embryonic outlines preserved in exceptionally rare specimens provide a glimpse of a life cycle completed entirely in the marine environment. A mother did not need a shoreline, a nest, or a return journey over land. Her offspring began life, where the adults already hunted and traveled. By the later Cretaceous, this combination of flexible jaws, internal gripping teeth, powerful tails, and fully aquatic reproduction had produced one of the most successful marine reptile radiations known from the fossil record. Mosasaurs were still unmistakably reptiles, yet almost every part of their anatomy had been reshaped around the demands of the sea. Their lineage had taken an inheritance from lizards and snakes and carried it into an environment where a flexible jaw became something entirely new. The chalk beneath the ancient Moss River holds an early chapter in the history of marine fossils. In the 18th century, miners and naturalists encountered enormous bones embedded in the pale rock of the Netherlands, remains belonging to a creature later named Mosasaurus hoffmanni. Its genus name, derived from the Meuse River, became a fitting label for a reptile that would eventually be recognized as one of the greatest hunters of the Cretaceous seas. At its largest known size, Mosasaurus hoffmanni reached about 17 meters, about 56 feet, in length, with mass estimates approaching 15 metric tons, about 16 and one-half tons. Other body proportion models have produced estimates around 15,000 kilograms, about 33,000 pounds. Its proportions made it longer than many modern buses and gave it a presence unlike the more compact predators that had ruled earlier seas. Yet length alone does not explain its ecological success. The animal combined a powerful tail, paddle-like limbs, a flexible spine, and an exceptionally large skull, allowing it to travel through open water while remaining capable of sudden changes in direction. Its appetite appears to have been unusually broad. Fossil stomach contents and associated prey remains indicate that Mosasaurus consumed fish, sharks, seabirds, sea turtles, plesiosaurs, and smaller mosasaurs. Such a varied menu placed almost every major component of its marine ecosystem within reach. The predator did not depend on one narrow food source. It could move between different prey communities as opportunities changed, making its ecological role broader than that of many specialized hunters. Its broad diet also reduced dependence on any single seasonal abundance, allowing this immense reptile to remain flexible within a changing marine ecosystem over time. Among the most intriguing evidence are injuries preserved on the bones of other large mosasaurs. Deep punctures and gouges occur on skulls of Mosasaurus and Tylosaurus, with dimensions and spacing consistent with bites from animals of similar size. In some specimens, new bone formed around the damaged areas, showing that the wounds were sustained while the animal was alive and survived long enough for healing to begin. These marks reveal that competition within the group could become physical, with enormous reptiles capable of turning their jaws against members of their own lineage. Even hard-shelled prey left a record of those encounters. Fossilized ammonite shells sometimes preserve curved impressions made by mosasaur teeth, including shells exceeding 1 meter, about 3 feet, in diameter. The marks show that the jaws could apply enough force to damage heavily reinforced shells, opening access to prey protected by mineralized armor. Each damaged shell is a small record of a feeding attempt preserved long after the animal that made it disappeared. The same Cretaceous world also contained Tyrannosaurus rex on land. That animal reached roughly 12 meters, about 40 feet, and may have weighed around 8,000 kilograms, about 9 tons, while Mosasaurus occupied the water at a scale approaching 17 meters, about 56 feet, and 15 metric tons, about 16 and one-half tons. Their lives overlapped in geological time, yet their hunting worlds remained separated by the shoreline. One pursued terrestrial animals across continental landscapes, while the other moved through an ocean filled with prey that no land predator could reach. Mosasaurus, therefore, represented more than enormous size. Its fossil record shows a predator willing to exploit nearly every available source of animal protein, capable of opening armored prey and enduring attacks from its own kind. Within that broad family, however, Another mosasaur developed a feeding strategy that left an especially intimate record, preserved inside the remains of a fossil found far inland. The western interior seaway once divided North America along a broad marine corridor, leaving behind layers of chalk that now preserve fragments of the world that lived above them. During the late Cretaceous, this inland ocean stretched more than 3,000 kilometers, about 1,900 miles, from the Arctic region toward the Gulf of Mexico, reaching roughly 1,000 kilometers, about 620 miles, across at its broadest. In places, its water may have descended nearly 1 kilometer, about 3,300 feet beneath the surface. What is now Kansas, Nebraska, and the Dakotas once lay beneath warm water filled with ammonites, fish, turtles, seabirds, and enormous marine reptiles. Moving through that immense basin was Tylosaurus, one of the most formidable mosasaurs known from North American fossils. The largest confirmed individuals approached 14 meters, about 46 feet in length, making them among the dominant hunters of the seaway. Kansas recognizes Tylosaurus as its state fossil, a fitting reminder that the landscape surrounding modern prairie towns once belonged to an oceanic ecosystem whose largest predator could cross the same region without ever touching land. Its most distinctive adaptation appeared at the very front of the skull. Unlike Mosasaurus, Tylosaurus had an elongated, reinforced snout without teeth at its tip. The structure formed a hardened prow, capable of striking prey before the jaws closed around it. Fossil specimens preserve injuries and deformation around these snouts, evidence consistent with repeated impacts. Rather than relying solely on the teeth to begin an attack, Tylosaurus could use its head as a blunt instrument, delivering a sudden collision that may have stunned or disrupted another animal before feeding began. The stomach of one South Dakota specimen preserves an unusually rich record of what happened afterward. Inside, the body cavity were remains of a mosasaur roughly 2 meters, about 6½ feet, long, along with the diving bird Hesperornis, a large bony fish called Bananogmius, and possible shark remains. 4 very different prey animals had entered the same digestive system. The finding turns a generalized idea about mosasaur feeding into something more tangible, a single meal record assembled from several branches of the marine food web. Another clue comes from impressions left by scales. Some Tylosaurus fossils preserve a darker upper surface and a lighter underside, a pattern known as countershading. The arrangement would have reduced the contrast between the animal and the surrounding water, depending on whether prey viewed it from above or below. Modern great white sharks use a similar pattern, yet the resemblance is the product of convergent evolution, separated by roughly 80 million years. 2 unrelated predators arrived at a similar solution because the physics of open water offered them the same advantage. Along the western margin of the seaway, Tyrannosaurus rex occupied terrestrial habitats while Tylosaurus moved through the water. Their ranges could approach within roughly 160 kilometers, about 100 miles, yet their lives unfolded in different dimensions. One hunted across shorelines and floodplains, while the other followed currents, schools of fish, and the movements of marine reptiles. The coastline formed a narrow boundary between 2 immense predators, each shaped by an ecosystem the other could never enter. The seaway itself was temporary, its waters eventually retreating as the continent rose and the climate changed. Its sediments remained, preserving the traces of animals that once crossed an ocean where plains now stretch beneath the sky. Within those deposits, Tylosaurus appears not as an isolated monster, but as one part of a layered community, sharing the water with creatures whose bodies occupied entirely different solutions to life at sea. A strange proportion defines Elasmosaurus before any measurement is taken. Its body was compact, its head modest, and then the neck continued, vertebra after vertebra, until the animal seemed almost divided between a swimmer and an extraordinarily extended reach. The specimen was discovered near Fort Wallace, Kansas in 1867 by Army surgeon Theophilus Turner, and Edward Drinker Cope formally described it the following year. What emerged from the fossils was an animal roughly 14 meters, about 46 feet, long, with more than half that length belonging to the neck. Within that elongated structure were 72 cervical vertebrae, the individual bones forming the neck. No other known animal is recognized as having more cervical vertebrae. Together they produced an elongated framework, approximately 7 meters, about 23 feet, long, longer than the body and tail combined. Yet the neck was not simply an extravagant extension. Its many small joints distributed movement across the entire structure, allowing the head to shift position without requiring one enormous bend at a single point. The result was a long biological reach, whose movement could be spread through dozens of separate segments. That arrangement mattered because Elasmosaurus did not need to bring its entire body toward every meal. Fish moving through the upper water could remain within reach, while the heavier torso stayed farther away. The head could advance independently, approaching from an angle that reduced the disturbance created by the animal's main mass. In this sense, the neck became part of the hunting strategy itself, extending the distance between the predator and the motion that might reveal it. Modern computer simulations have added another layer to the picture. A study from the University of Bristol published in 2022 found that the enormous body of Elasmosaurus could have provided the stability needed to control such an unusually long neck. A smaller body would have been more easily displaced whenever the head changed direction, but greater mass resisted that reaction. The animal's size therefore helped support the very feature that made its anatomy unusual. The neck was not merely tolerated by the body helped make the neck workable. Stones preserved inside some plesiosaur fossils offer another glimpse of life beneath the surface. These gastroliths, swallowed stones, may have contributed to ballast, helping the animal maintain depth while moving through the water column. For a predator carrying a long neck ahead of a comparatively compact body, controlling buoyancy and position would have been valuable. Below schools of fish, the animal could hold its body at a useful depth while the head explored the water above, where prey might be outlined against the brighter surface. The story of Elasmosaurus also carries a distinctly human imperfection. When Cope first assembled the skeleton, he placed the skull at the wrong end, attaching it to what was actually the tail. The error was eventually identified by his rival, Othniel Charles Marsh, and the public correction became part of a much larger scientific rivalry. Behind the dispute remained something more enduring, a fossil animal whose anatomy challenged even experienced observers. Its neck was so unlike the proportions of familiar vertebrates that understanding the creature required letting the bones dictate the shape, one connection at a time. Elasmosaurus therefore occupied an unusual place in the Cretaceous Sea, not through crushing jaws or enormous teeth, but through controlled reach, stability, and an anatomy built around distance. Its 72 neck vertebrae transformed a simple act of movement into an elaborate chain of small adjustments, allowing a head to travel far beyond the body that carried it with remarkable economy beneath the ocean surface. Not every dominant hunter of the western interior seaway carried a reptile's skeleton. Xiphactinus belonged to the bony fishes, yet its proportions gave it the presence of something far larger in the imagination. Growing to roughly 6 meters, about 20 feet, it was among the largest predatory bony fish of the late Cretaceous, occupying waters also traveled by Tylosaurus and Elasmosaurus. Its body was deep and streamlined, built for sudden movement, while a broad mouth opened around rows of long, conical teeth. Those teeth were shaped less for slicing than for gripping, allowing Xiphactinus to seize prey and keep hold as both animals struggled through the water. For much of its existence, roughly from 100 million to 66 million years ago, it moved through a seaway where visibility, currents, and shifting schools of prey could change the value of speed from one moment to the next. Its broad tail and muscular body suited that world, giving it the ability to accelerate toward prey before closing the distance with its oversized gape. Fossils preserve the variety of that appetite. Smaller fish formed an important part of its diet, but remains of sea turtles and the diving bird Hesperornis have also been found associated with its stomach contents. Some evidence even suggests that pterosaurs occasionally entered its feeding range, perhaps when they skimmed too close to the surface. Such remains place Xiphactinus in the middle of a remarkably connected food web, where creatures adapted to air, open water, and the seafloor could all become part of the same predator's diet. The most revealing specimen came from Kansas, where paleontologist George F. Sternberg recovered a Xiphactinus containing another fish almost perfectly preserved inside its body. The predator itself measured about 4 meters, about 13 feet, while the swallowed Gillicus arcuatus reached nearly 2 meters, about 6 feet, within the stomach cavity. The smaller fish was still recognizable in extraordinary detail, its body arranged inside the larger animal as though the moment of feeding had been paused before digestion could erase it. The specimen suggests that the meal may have been more than Xiphactinus could safely manage. A large prey animal struggling during swallowing could damage internal organs, and the predator appears to have died soon after feeding. The fossil does not preserve the final movement itself, but the anatomical arrangement leaves a striking record of how closely feeding and mortality could become connected. That pattern was not unique. At least a dozen Xiphactinus specimens have been discovered with substantial prey remaining largely undigested within their body cavities. Some contained animals so large that their meals occupied a remarkable portion of the available internal space. Each fossil captures a brief interval between successful capture and completed digestion, revealing a predator whose feeding strategy carried an unusual physical risk. The significance lies not simply in the size of the meals, but in the limits imposed by the body itself. A hunter can become efficient at pursuing prey and still encounter a boundary when the prey is swallowed. Xiphactinus possessed the jaws, teeth, and appetite to take animals of considerable size, yet digestion required space, movement, and time after the struggle had ended. A meal that could be captured in moments might remain physically dangerous long afterward. Along the ancient seaway, this created a curious vulnerability within an otherwise capable predator. Xiphactinus could chase, seize, and consume animals that belonged to several different parts of the ecosystem, but some of those victories appear to have carried consequences that the fossil record preserves with unusual clarity. Its body became a temporary archive of the final meal, holding prey in place long after the water above the ancient seafloor had changed and the living animal itself had disappeared. The end of the great marine reptile age arrived from above, but its consequences unfolded through the water. 66 million years ago, an asteroid roughly 10 kilometers, about 6 miles, across struck the shallow seas near what is now the Yucatan Peninsula of Mexico. It was moving at approximately 72,000 kilometers per hour, about 45,000 miles per hour, when it reached the surface, releasing an amount of energy beyond any ordinary terrestrial comparison. Near the impact site, rock was crushed, melted, and thrown upward in a vast plume. Water was displaced across the surrounding sea, sending enormous waves outward through the Gulf of Mexico and beyond. Farther away, heated debris returned through the atmosphere, while fires spread across landscapes already disturbed by the violence of the collision. Yet the most persistent damage was not the first wave, nor the falling debris. It came afterward, when dust, sulfur-bearing material, and other particles remained suspended high above the surface. Sunlight reaching the planet was reduced for an extended period, and the consequences reached the ocean through its smallest inhabitants. Phytoplankton depend upon sunlight to build organic matter, turning light into the energy that supports nearly every larger creature above them. As their populations declined, the zooplankton that fed upon them lost their foundation. Small fish then lost much of their food, followed by larger fish and the predators that depended upon them. The collapse moved upward through the food web, not as a single event, but as a widening absence of nourishment. For animals at the top of the marine hierarchy, size had become a burden. Mosasaurs required substantial quantities of food, as did the remaining plesiosaurs and enormous predatory fishes such as Xiphactinus. Their bodies were adapted to an ocean filled with abundant prey, yet abundance could not return, while sunlight remained limited. One by one, the lineages that had shaped the late Cretaceous seas disappeared from the fossil record. Every known species of mosasaur vanished. The surviving plesiosaur lineages vanished as well, along with Xiphactinus and many other marine organisms that had occupied the seaway. The great marine reptile dynasty had endured for more than 180 million years, but geological time compresses its final chapter into a remarkably narrow boundary. That boundary can still be touched in rocks around the world. A thin layer enriched in iridium appears within marine sediments and exposed terrestrial deposits, marking the transition between the Cretaceous and the Paleogene. Iridium is scarce at Earth's surface, but more common in extraterrestrial material, giving the layer a chemical signature that connects distant landscapes to the same planetary event. Beneath it lies a world filled with familiar giants. Above it, the composition of life changes. Survival favored different qualities. Smaller animals generally required less food, could shelter from unstable conditions, and could exploit whatever resources remained. Turtles endured. Some sharks endured. Crocodilians endured. Their survival did not mean the oceans immediately recovered. Instead, the ecological space, once occupied by giant marine reptiles, remained open, while food webs began reorganizing around the organisms that had made it through. The sea therefore carried the asteroid's legacy long after the impact itself had faded from the landscape. Recovery began unevenly, with some coastal habitats rebuilding before the open ocean could support larger predators again. Its chemistry recorded the disturbance, its sediments preserved the boundary, and its surviving animals carried the first threads of a different marine future. The age of giant reptiles had not simply been interrupted. Its foundation had been removed, leaving an ocean whose next great predators would arise from entirely different branches of life. A fossil can preserve the curve of a tooth, the texture of a scale, or the shape of a bone, yet leave almost everything around it to time. Paleontology is therefore built upon fragments, and every fragment carries a strange imbalance between what once existed and what remains. The prehistoric ocean was filled with bodies that vanished without leaving a recognizable trace, while a fortunate few became the fossils through which entire worlds can be reconstructed. Dunkleosteus is one of the clearest examples. Its immense armored head is known in remarkable detail, including the sharpened bony plates that formed its feeding apparatus. Behind those plates, however, much of the animal was cartilage and soft tissue, material with a far lower chance of surviving burial and mineralization. Estimates of its maximum size have therefore changed as scientists have learned more about how its body may have been proportioned. The missing parts are not merely an inconvenience, they place a boundary around what can honestly be known. Helicoprion leaves an even stranger record. Its most recognizable feature is a spiral tooth whorl, a structure that could survive while the rest of its cartilaginous skeleton disappeared. From that single coil, scientists have reconstructed aspects of feeding and anatomy, but the animal itself remains partly hidden behind the one structure that happened to endure. The fossil is a reminder that preservation can make one feature seem more important simply because that feature lasted. Ichthyotitan tells a different story. Its enormous lower jaw fragments were found in Somerset, England, and the animal was named in 2024. Scaling those bones against related giant ichthyosaurs suggests a body around 25 meters, about 82 feet, long, although no complete skeleton exists. The estimate is therefore a reconstruction built from comparison, not a measurement taken from an intact animal. Even an enormous creature can reach the scientific record through only a few pieces of bone. Exceptional preservation sometimes depends upon the place where an animal died. The fine-grained sediments around Holzmaden in Germany preserved remarkably detailed outlines of several ichthyosaurs, including traces of body shape and soft tissues that would normally disappear. Such preservation requires unusual circumstances, rapid burial, suitable sediment, and chemistry that discourages decay. In most ancient marine deposits, those conditions never aligned, leaving only scattered bones or nothing at all. That unevenness changes the meaning of every giant fossil. The animals known to us are not necessarily the largest predators that ever moved through prehistoric seas. They are the animals for which geology happened to provide evidence strong enough to survive millions of years and then be discovered by another species entirely. Even museums can become part of that chain of chance. In 2026, vertebrae from the giant shark Ototus megalodon, long thought lost after a museum move in 1989, were rediscovered in Denmark. The largest vertebra measured 23 centimeters, about 9 inches, across, providing unusually valuable evidence because shark skeletons are largely cartilage. Their return from a storage shelf did not create a new animal. It restored a piece of an old one that had briefly disappeared from science. The fossil record is therefore less like a complete catalog and more like a scattered collection of surviving pages. Some pages preserve anatomy, others preserve meals, injuries, pregnancies, or the chemistry of ancient environments. Between them lies an immense unwritten space, occupied by creatures whose bodies returned to the sea floor and left nothing recognizable behind. Every discovery narrows that darkness by a small degree, while every missing skeleton reminds us that the prehistoric ocean was always larger than the evidence we possess. Nothing in the prehistoric ocean evolved alone. Every advantage carried a cost, and every new defense created another opportunity for something else to improve. Across hundreds of millions of years, bodies became records of these exchanges, shaped not by a single predator, but by generations of pursuit, escape, resistance, and adaptation. Among the armored fishes of the Devonian seas, Dunkleosteus occupied a world where protection itself became part of predation. Its enormous plates formed a powerful defensive structure, while its jaws could open and close with remarkable speed. Sharks already existed beside these armored competitors, and their later history reflects a broader evolutionary pattern in which lighter bodies, replaceable teeth, and flexible skeletons offered advantages that rigid armor could not provide. The modern shark body was not created by one ancient rival, but it emerged through a long sequence of pressures in which predators helped shape which designs remained useful. During the Jurassic, ichthyosaurs carried a different record of pressure. Their bodies became increasingly streamlined, with narrow profiles and powerful tails suited to sustained swimming. Pliosaurs occupied the same marine world, creating competition between predators that could not simply ignore one another. Faster acceleration, efficient turning, and the ability to reach deeper water offered ways to reduce encounters with larger hunters. Evolution did not need to produce a perfect escape strategy. It only needed to favor the individuals whose bodies made survival slightly more likely. The same principle can be seen in marine reptiles that carried armor rather than speed. Sea turtles survived alongside mosasaurs, animals capable of biting through substantial shells. Some late Cretaceous turtle lineages developed increasingly robust shell structures, although shell thickness varied with ecology and ancestry rather than following one simple progression. Protection was never free. Additional mineralized tissue required resources, increased mass, and altered movement, yet a stronger shell could turn a vulnerable body into a difficult meal. For long-necked plesiosaurs, the balance was different again. Their unusual anatomy placed the vulnerable body behind an extended neck, allowing the head to investigate spaces where the larger torso remained farther away. Kronosaurus and other pliosaurs could prey upon these animals, as suggested by bite damage and injured remains. Such pressure may have favored maneuverability, controlled flipper movements, and hunting strategies that allowed plesiosaurs to approach prey without exposing their entire bodies at once. Their anatomy was not simply an elegant accident, it existed within an ocean where other bodies were constantly testing its limits. Above the surface, another predator relationship unfolded. Xiphactinus could seize animals moving close to the water, including seabirds such as Hesperornis. These flightless diving birds had lost the ability to escape through flight, but their powerful limbs and streamlined bodies made them capable swimmers. Diving into the water placed them within a different ecological world, where the same environment that offered food also contained predators. Their anatomy reveals how survival could depend upon moving between layers of the same habitat. Modern oceans still carry echoes of those ancient pressures. Dolphins possess bodies built for rapid movement and precise control. Sea turtles can remain submerged for long periods, balancing oxygen storage with energy demands. Schooling fish coordinate their movements in ways that reduce the chances of any single individual being captured. Whales carry massive skulls and specialized feeding structures suited to very different forms of predation. None of these traits was designed by a vanished monster, yet each belongs to a lineage shaped by countless encounters with predators, competitors, and changing environments. The ancient hunters disappeared, but evolution does not erase pressure simply because the animal applying it is gone. Their influence can remain embedded in the bodies of descendants, carried forward through anatomy, behavior, and the enduring mathematics of survival. On land, every extra kilogram becomes a structural problem. A predator must carry its own weight through every step, transmitting force from muscle to bone and from bone into the ground. As bodies grow, those forces rise, joints endure greater stress, and the skeleton must become stronger without becoming so heavy that movement becomes inefficient. Size therefore brings a growing architectural cost. Tyrannosaurus rex approached the practical upper range for a giant terrestrial hunter. Its massive legs and reinforced joints supported a body measured in tons, while its movement depended upon keeping that great structure balanced over a relatively small number of weight bearing limbs. Making the animal substantially larger would not simply require adding more muscle. The entire framework would need to change, from bone thickness to joint geometry, tendon strength, and the mechanics of each stride. Eventually, the animal would spend too much of its available energy carrying itself. Water changes that equation at the most fundamental level. Buoyancy carries much of an animal's mass, allowing enormous bodies to remain suspended without placing their full weight upon a skeleton. A marine predator can therefore devote more of its biological budget to jaws, muscles, sensory organs, and digestive capacity. Its body still faces resistance from the water, but that resistance is different from the relentless burden of gravity acting through a terrestrial skeleton. The fossil record repeatedly reflects this freedom. Dunkleosteus grew into an armored predator for which no comparable land hunter existed in its Devonian world. Pliosaurs later reached extraordinary dimensions, their bodies supported by seawater, while their jaws became increasingly massive. Predator X, formerly known as Pliosaurus funke, occupied the Jurassic seas at a scale that had no close terrestrial counterpart. Mosasaurus hoffmanii could reach roughly 17 meters, about 56 feet, and masses of approximately 15 metric tons, about 33,000 pounds. While moving through an environment that carried much of that enormous weight, the advantage extends beyond body size. Land is mostly a two-dimensional hunting surface. A predator can move forward, backward, and around obstacles, but the ground ultimately defines where its body can go. Water removes that boundary. Prey may pass above, below, or around a hunter, and predators can exploit depth as readily as distance. A body can rise beneath a target, descend away from danger, turn through a vertical arc, or approach from an angle unavailable to most terrestrial hunters. That three-dimensional space also rewards senses capable of interpreting movement through water. Pressure changes, chemical traces, vibrations, and subtle shifts in surrounding currents can reveal an animal that cannot yet be seen. The ocean therefore encourages a different kind of predatory specialization, one in which detection, maneuverability, acceleration, and body size can develop together. None of this means the ocean automatically creates giants. Marine life still faces limits from oxygen, food availability, temperature, reproduction, and the energetic cost of moving through dense water. Yet buoyancy removes one of the most severe constraints imposed on large terrestrial predators. Once that burden is reduced, evolution has more room to experiment with scale. Across the vertebrate fossil record, the pattern appears again and again. Different continents, different oceans, different eras, and entirely unrelated lineages repeatedly produced predators larger than the great hunters walking on land beside them. The names changed, the bodies changed, and the methods of hunting changed, but the physical opportunity remained. Water could support the mass that land had to carry, and that difference gave evolution a larger canvas on which to build its most formidable predators. The ocean kept offering predators room to become larger, heavier, and more specialized without first asking them to carry themselves across solid ground. The ocean keeps no throne, yet across deep time, one creature after another has occupied the highest place in its food web. What changes is not the presence of a dominant hunter, but the form that dominance takes. Over hundreds of millions of years, Evolution repeatedly arrived at enormous predators, each shaped by a different combination of anatomy, prey, and opportunity. In the Devonian seas, Dunkleosteus carried its weapons in armored plates that formed the front of its skull. Later, Helicoprion developed a feeding structure unlike anything that had come before, while its relatives occupied an ocean transformed by changing coastlines and marine communities. The Triassic brought giant ichthyosaurs, whose streamlined bodies and enormous eyes suited a world where pursuit could unfold through open water. By the Jurassic, pliosaurs had become broad-headed hunters with powerful jaws and compact bodies built for sudden acceleration. Then the Cretaceous gave the seas mosasaurs, reptiles whose ancestors had returned to the water and whose descendants diversified into an astonishing range of forms. The differences are more revealing than the succession itself. One lineage relied on armor and crushing surfaces. Another carried a spiral tooth structure within the lower jaw. Giant ichthyosaurs combined enormous bodies with specialized senses and efficient swimming. Pliosaurs concentrated their power at the front of the skull, turning the head into a dense engine of capture. Mosasaurs reshaped the reptilian body for marine life, combining flexible jaws, grasping teeth, and powerful tails. None of these solutions needed to resemble the one before it. Natural selection works with inherited structures, available prey, changing climates, and the physical conditions of each ocean. When an extinction removes a dominant lineage, it does not leave behind a blueprint for its replacement. It leaves ecological space. Other animals, already present in smaller roles, can expand into that space, changing their bodies as generations pass. The Permian extinction demonstrates how profound such resets could become. Roughly 96% of marine species disappeared, yet the seas eventually developed new communities and new predators. Much later, the extinction at the end of the Cretaceous erased mosasaurs, plesiosaurs, and many other marine lineages. The vacancy did not remain permanent. Sharks, marine reptiles that survived, turtles, bony fish, and other survivors inherited altered ecosystems and gradually formed new relationships within them. Across this immense succession, the ocean behaves less like a kingdom with a permanent ruler and more like a landscape, continually rearranging its possibilities. A predator becomes dominant because its body fits a particular moment, then that moment changes. Coastlines shift, temperatures rise and fall, prey communities reorganize, new competitors appear. Eventually, another lineage finds an opening that had not existed before. The names changed with the chemistry of the seas, the shape of continents, and the creatures available to hunt, but the pressure remained. Each generation inherited a world already crowded with life, then altered its place within that world through small anatomical advantages accumulated over immense spans of time. Scale emerged from those countless adjustments, not from any single moment of design. Every dynasty was temporary, but the pattern was persistent. The bodies vanished, their lineages ended, and their oceans were transformed, yet the underlying ecological vacancy remained something evolution could fill again. The history of these predators is therefore not a procession of identical monsters, but a record of nature repeatedly solving the same ecological problem with entirely different materials. Deep time becomes stranger when the distances between events are measured not in miles, but in vanished worlds. The age of Dunkleosteus lies so far behind the reign of Mosasaurus that the later predator would have been separated from its Devonian predecessor by roughly 290 million years. That interval is itself comparable to the span from the late Cretaceous to the present day. For a human mind, both distances are almost equally difficult to hold. The creatures encountered across this story, therefore, belonged to no single age of monsters. Dunkleosteus lived in a Devonian ocean long before the first dinosaurs appeared. Ichthyotitan belonged to a Triassic world that emerged after the most severe extinction in Earth's history had already transformed marine life. Mosasaurus arrived much later, in seas filled with lineages that had themselves descended through countless earlier changes. Between these animals stretched immense intervals during which coastlines moved, mountains rose and eroded, climates shifted, and entire families appeared, diversified, and disappeared. Human history occupies only a minute fraction of that scale. The oldest cities, written records, dynasties, migrations, and monuments all belong to an almost imperceptible recent layer. Even the existence of our species is confined to the closing portion of the story. When measured against deep time, the difference between an ancient empire and the present becomes small enough to disappear into the same brief gesture. The Permian extinction offers another way to sense the distance. It occurred about 252 million years ago, long before the asteroid impact that ended the Cretaceous. Yet that earlier catastrophe and the later extinction are separated by more than 200 million years, a span containing the rise of dinosaurs, the spread of flowering plants, the opening and closing of oceans, and the evolution of countless marine communities. What feels like one continuous prehistoric age is actually a sequence of worlds, each lasting longer than civilizations have existed. Through all those changes, something remarkably familiar persisted. Water moved from ocean to atmosphere, from clouds to rain, through rivers, ice, groundwater, and back into the sea. Individual water molecules are constantly exchanged among these reservoirs, and many have existed for immense spans of geological time. Some of the molecules surrounding a swimmer today may once have passed through ancient organisms, though there is no way to identify a particular molecule or trace its complete journey. The continuity is physical rather than sentimental. Over roughly 375 million years, the water has remained within a planetary cycle, even as the creatures living within it changed beyond recognition. The oceans have changed in chemistry, temperature, depth, circulation, and biological richness, yet the fundamental substance of the sea has remained part of the planetary cycle. Water has crossed the boundaries between vanished ecosystems without remembering them, carried by evaporation, precipitation, currents, glaciers, and the slow rearrangement of continents. That makes the present ocean part of the same planetary process that once supported Dunkleosteus, giant ichthyosaurs, plesiosaurs, and mosasaurs. Their bodies disappeared, their environments were transformed, and their lineages ended, but the water continued moving through the Earth system. A drop reaching the shore today may have followed a path through clouds, ice, rock, and living tissue that began long before human beings existed. That is why deep time is not simply a distant past stacked behind the present. It is an immense continuity in which old materials persist while forms change around them. The predators vanished, the seas reorganized, and the continents traveled across the planet, yet the cycle itself remained in motion, carrying fragments of one world into the next. A fragment of ancient bone can spend decades as an ordinary object before anyone recognizes the story held inside it. On a beach in Somerset, England, that story began with Ruby Reynolds, who was 11 years old when she noticed a large jaw fragment eroding from the shoreline in 2020. The specimen belonged to an ichthyosaur, and after years of study, it became part of the evidence for Ichthyotitan severnensis, a species that may represent the largest marine reptile formerly described. The discovery was not made in a distant expedition or beneath some untouched landscape. It emerged from a place where people had been walking for generations, waiting for the right eyes to notice what the weather had exposed. The significance grew as researchers compared the fragment with related fossils and reconstructed the animal's proportions. Its scale was inferred rather than measured from a complete skeleton because no complete body has been recovered. That distinction matters. Paleontology often advances through fragments, with anatomy rebuilt from the relationships among bones, proportions, and close relatives. A single piece can therefore alter the boundaries of what scientists consider biologically possible, while still carrying uncertainty that remains part of the evidence. Other discoveries have arrived through a different kind of transformation. In 2022, computational modeling from the University of Bristol examined the long neck of Elasmosaurus and challenged an assumption that had shaped interpretations for generations. Rather than treating its enormous body as a burden that made the neck impractical, the analysis showed that substantial body mass could provide stability during movement. The result did not change the fossil itself. It changed the way its anatomy could be understood, demonstrating how an old specimen can yield new information when modern methods ask more precise questions. Technology can reveal another layer without adding a single new bone. In 2024, imaging of a Dorset pliosaur skull examined internal structures that could not be seen from the surface. Computed tomography revealed an extensive network of passages associated with blood vessels around the snout, providing evidence for a sophisticated sensory region. The skull had been available to science for years, yet its hidden architecture remained inaccessible until imaging allowed researchers to examine the fossil from within. The same year brought the formal scientific description of Ichthyotitan severnensis in the journal Public Library of Science 1. A specimen first noticed on a beach had become evidence for a new species, and with it, a revised understanding of the upper limits reached by marine reptiles. The sequence is remarkably human: observation, curiosity, comparison, technology, and patient analysis, gradually turning a fragment into knowledge. Museums preserve another layer of possibility. Drawers and storage cabinets contain specimens gathered by earlier generations, including material that may never have received modern examination. Some fossils lack the features that once attracted attention. Others were collected before digital imaging, three-dimensional reconstruction, or improved statistical methods became available. A specimen can therefore remain physically unchanged while its scientific meaning evolves around it. The rock itself also continues to expose new material. In Queensland, the discovery of Kronosaurus remains associated with a sea turtle, preserves a feeding episode from an ocean that disappeared long ago. Along coastal cliffs, riverbanks, quarries, and eroding shorelines, weather continues to uncover fragments at a pace no collection can predict. Each new specimen adds only a small piece, yet the picture grows because those pieces can connect with evidence already preserved elsewhere. A jaw can extend a known range. A skull can reveal an unseen sensory structure. A fragment can establish a species. A familiar fossil can become new again when viewed through better tools. The creatures are gone, but their evidence is not finished. Every exposed layer carries the possibility that something overlooked will become legible, and that another fragment will gently widen the boundaries of what the ancient ocean was capable of producing. The prehistoric ocean survives in places that no longer resemble the sea. Its remains form cliffs, hills, roads, quarries, and fields, folded into landscapes where waves have not reached for millions of years. What was once a living marine environment has become part of the solid earth, preserved not as a single fossil, but as an entire layer of the planet. Along the coast of southern England, the white cliffs of Dover rise from chalk deposited during the Cretaceous. Much of that chalk formed from microscopic calcareous plates produced by tiny marine organisms called coccolithophores. Generation after generation, these plates settled onto the seafloor, accumulated, and became sediment. Later, geological forces lifted and tilted the deposits, exposing them above the water. The cliffs therefore preserve an ocean at a scale far larger than any individual skeleton. Within their pale stone is evidence of countless drifting organisms, changing currents, ancient chemistry, and the slow accumulation of life itself. Across central Kansas, another former sea lies beneath the prairie. The Smoky Hill chalk and the rock formations around Monument Rocks were deposited in the Western Interior Seaway, the inland marine system that once stretched across much of North America. The surface today is grassland and farmland, but beneath it are sediments formed in water that supported Tylosaurus, Xiphactinus, plesiosaurs, sharks, turtles, and countless smaller organisms. Fossils from these deposits preserve teeth, vertebrae, shells, bones, and traces of feeding, turning an ordinary landscape into a geological record of an ancient marine ecosystem. Near Fort Wallace, the fossils of Elasmosaurus emerged from this same broad geological region. Other discoveries from Kansas include remains of Tylosaurus, Xiphactinus, sharks, and numerous marine invertebrates. Their presence does not mean the sea moved inland recently. It records a much older arrangement of continents, coastlines, and sedimentary basins when water covered land that now appears impossibly distant from any modern ocean. Ammonites extend that connection across the world. Their coiled shells occur in exposed rock, quarry walls, road cuts, and building stone, sometimes far from the places where the animals originally lived. These shells belong to cephalopods that inhabited ancient seas and became buried as sediments accumulated around them. Over geological time, their mineralized remains became part of limestone and other rocks, allowing pieces of former marine ecosystems to enter the built environment. Even the color carries a memory of that setting. Chalk is pale because its mineral framework is dominated by calcium carbonate, giving these deposits their familiar whiteness. Under different conditions, the same ancient seas could leave darker mudstones, sandstones, or richly fossiliferous limestone, preserving different portions of the environments in which marine life lived. A garden wall can therefore contain the shell of an animal that lived beside predators now separated from us by an immense stretch of time. A road cut can reveal a layer formed beneath water that once covered a continent. A cliff can preserve the accumulated remains of organisms so small that individual bodies are invisible, yet whose collective contribution became a landmark. The transformation is more than preservation. It is a change of identity. A seafloor becomes stone. Stone becomes a cliff, a quarry, a wall, or a field beneath which fossils remain embedded. The ocean that once surrounded these animals has changed shape many times, but parts of its physical record remain integrated into the landscapes people inhabit every day. The prehistoric sea is therefore not confined to museum halls or distant coastlines. It is present in the material of the world itself, spread through rock and soil, carried upward by geology, and exposed by erosion. What disappeared as living ocean life endured in another form, compressed into the ground beneath a world that came much later. Seen across deep time, the pattern becomes less like a collection of extraordinary animals and more like a recurring property of the sea itself. For hundreds of millions of years, whenever marine ecosystems had enough time to rebuild, large predators appeared again, occupying the upper reaches of the food web with bodies shaped by entirely different histories. Dunkleosteus reached that position through armor and immense jaw mechanics. Later, marine hunters found other solutions, developing streamlined bodies, elongated skulls, powerful flippers, flexible jaws, or specialized teeth. Their anatomy changed from dynasty to dynasty, yet the ecological role remained recognizable. Something large occupied the upper levels, something capable of pursuing substantial prey across a three-dimensional environment where movement was not confined to a surface. Water changes the mathematics of size. On land, every additional kilogram of tissue becomes another burden that bones, joints, tendons, and muscles must carry against gravity. A terrestrial predator must generate enough force to support itself while standing, accelerate its body while running, absorb repeated impacts, and maintain stability over uneven ground. Increasing body size, therefore, brings structural costs that eventually become difficult to overcome. In the sea, buoyancy carries much of that burden. A large animal still needs strong muscles, a substantial energy supply, and efficient ways to move through water. But its skeleton does not bear its entire body weight in the same way. This allows evolution to devote more of the animal's physical budget to jaws, propulsion, sensory organs, and the machinery required to capture large prey. The advantage is not limitless, but it shifts the boundary. The ocean also offers a vast hunting volume. A predator can approach from below, descend beneath prey, rise toward the surface, turn through the water column, or disappear into deeper layers. Three-dimensional movement creates opportunities for ambush and pursuit that terrestrial predators encounter less often. Bodies can become longer, heavier, or more specialized without needing to remain balanced over four load-bearing limbs. Across roughly 375 million years of vertebrate marine history, that combination repeatedly produced extreme forms. The details were never identical. Environmental temperatures changed. Continents moved. Seas expanded and contracted. Prey communities transformed. Entire lineages vanished. Yet, after ecological upheavals, new predators eventually appeared within the reorganized food webs. The ocean itself covers about 71% of Earth's surface, nearly three-quarters of the planet, and its modern form rests upon a history extending far beyond the animals considered here. Oceans existed billions of years before vertebrates evolved jaws, before recognizable fish appeared, and before any predator possessed the anatomy seen in the fossils of this story. That longer history matters because the familiar giants were never the beginning. They were comparatively recent expressions of a much older biological process. Long before Dunkleosteus, marine ecosystems already contained hunters competing for energy, territory, and prey. Through the Cambrian and Ordovician periods, animal communities became increasingly complex, and predation became an important force shaping bodies, behavior, and ecological relationships. By the time vertebrates began producing the giants preserved in the fossil record, the sea had already spent immense spans of time refining the basic conditions that make large predation possible. Every generation inherited an environment where energy moved from microscopic producers through increasingly larger organisms, creating opportunities for hunters at the upper levels. The process has never required the same blueprint twice. Evolution can discard one solution and build another from different materials, different ancestors, and different circumstances. That is why the fossil record contains armored jawed fish, enormous marine reptiles, long-bodied hunters, and later predators, separated by immense stretches of time, yet linked by the same ecological opportunity. The engine is not a machine with gears or metal parts. It is sunlight entering the water, organisms capturing energy, predators converting that energy into movement, and generations reshaping bodies through survival and reproduction. It has been operating for almost 4 billion years, and the water still carries the same fundamental possibilities. The modern ocean gives us a strangely incomplete picture of what the sea can become. Its largest hunters are formidable, but compared with the giants preserved in ancient rock, the upper reaches of today's marine food web appear almost modest. No mosasaur moves beneath the waves now, no pliosaur patrols the continental shelves, and nothing resembles the armored bulk of Dunkleosteus. Orcas, reaching about 9 meters, roughly 30 feet, are among the most powerful living marine predators, combining speed, coordination, endurance, and remarkable intelligence. Large sharks occupy another branch of the modern predator guild, built for pursuit rather than the immense jaw architecture of many prehistoric hunters. Yet none approaches the extraordinary combinations of size and weaponry that appeared repeatedly in earlier oceans. Part of the reason lies in the event that ended the Cretaceous world. The extinction associated with the asteroid impact removed entire marine predator lineages, including the mosasaurs and plesiosaurs, while reorganizing nearly every level of the food web beneath them. What followed was not an immediate replacement. New ecosystems had to assemble from the surviving branches of life, and those survivors inherited oceans whose structure had been profoundly altered. Rebuilding an apex predator is not simply a matter of producing a larger animal. A giant hunter requires abundant prey, stable energy pathways, suitable habitat, and enough ecological time for natural selection to refine the anatomy that supports such a body. Its existence depends upon everything beneath it functioning at sufficient scale. When the upper food web collapses, rebuilding must begin much closer to its foundation. That makes the present ocean an unusual point on the long geological curve. 66 million years have passed since the great marine reptiles disappeared, an immense interval by human standards, yet only one chapter in the history of oceanic predation. Modern ecosystems have produced extraordinary hunters during that time, but they have not recreated a marine reptile dynasty comparable to the one that vanished at the end of the Cretaceous. The blue whale occupies an especially interesting place within this modern arrangement. Reaching about 30 meters, roughly 98 feet, it is the largest animal known to have lived, yet its enormous body is not built around killing large prey. It gathers tiny crustaceans called krill, filtering enormous quantities of seawater through baleen. Its size comes from the extraordinary abundance of small organisms available in productive waters rather than from dominance over other large animals. That distinction changes the way the modern sea should be imagined. A vast animal can exist without being a superpredator when enough energy enters the food web at lower levels. The blue whale demonstrates how different ecological pathways can produce extreme size, while the absence of giant marine hunters reveals how much the structure of an ecosystem matters to the animals living within it. For most of vertebrate history, the sea contained several layers of formidable predators, occupying different depths, habitats, and hunting strategies. Their presence shaped prey behavior, body structure, migration, and the distribution of other hunters. Today's ocean still contains intricate predator relationships, but the particular architecture inherited from the Cretaceous is gone. What we call a normal ocean is therefore only one moment in a much older sequence. The sea we know is not the permanent form of the ocean. It is one arrangement among many, produced by extinction, recovery, competition, climate, and evolutionary opportunity. Beneath its familiar surface lies a history in which the upper boundary of predation has repeatedly moved, vanished, and been rebuilt. And somehow, fragments of that vanished world remained long enough for us to find them, read them, and slowly reconstruct an ocean no human being ever witnessed. Nothing in the ocean carries a label from the creature that once moved through it. A drop of seawater does not remember Dunkleosteus passing above an ancient Devonian seafloor, or the first great marine reptiles crossing warm Triassic basins. Its atoms continue through the world in forms too ordinary to preserve a biography. Water rises from the surface as vapor, gathers within clouds, returns as rain, enters rivers, freezes into ice, seeps through rock, and eventually finds the sea again. Some of the same molecules that once occupied Cretaceous seas have passed through countless cycles since those ecosystems disappeared. The continents beneath them have changed shape, mountain ranges have risen and worn away, and coastlines have migrated across distances that would once have seemed permanent. The western interior seaway is now gone, replaced across much of its former extent by plains, hills, and river valleys. Yet the water that filled it did not vanish with the seaway. It became part of the larger circulation of Earth, moving between atmosphere, land, ice, and ocean. What was once beneath Tylosaurus became rain over forests, moisture in rivers, ice in distant mountains, and seawater moving through another coastline. Far to the north, the rocks of the Svalbard archipelago preserve another fragment of that changing geography. Jurassic marine sediments, their record seas that existed when enormous pliosaurs occupied northern waters. The shoreline has shifted, the climate has transformed, and the crust itself has moved through geological time. The water has simply continued its passage. Ocean circulation gives that passage structure. Differences in temperature and salinity alter density, allowing seawater to sink, rise, and travel through deep currents that connect distant basins. Wind moves the upper ocean. Tides respond to the gravitational influence of the moon and sun, and evaporation continually transfers water between sea and atmosphere. These processes operate on different timescales, yet together they keep the ocean in motion. There is something almost delicate about that continuity. The predators themselves were temporary arrangements of living tissue. Their teeth were replaced, their muscles aged, their bodies returned their elements to surrounding ecosystems. Their species disappeared, and eventually their bones became buried, altered, lifted, eroded, and exposed. The water around them followed another path entirely. It carried dissolved minerals from one shore to another. It entered clouds above extinct seas and fell onto landscapes where their descendants had never lived. It passed through organisms that evolved long after the great marine reptiles were gone. A molecule of water has no boundary marking one geological age from another, because Earth never draws such boundaries in the physical world. The ocean does not preserve the past by remembering it. The past survives because sediments, minerals, fossils, and layers of rock sometimes interrupt the movement long enough to leave a record. Water itself is different. It remains part of the present, continuously exchanged between the places where life has flourished and disappeared. That is why an ancient ocean can feel both impossibly distant and strangely close. The animals are gone, the shorelines are altered, the continents have wandered. Yet the planetary system that carried their seas forward is still operating around us, with sunlight lifting water from the surface, gravity returning it to the ground, and currents moving it through the depths. The ocean has no memory of the worlds it has carried. It only continues carrying the world that exists now. Every tide belongs to this present moment, even though the water itself has crossed boundaries between vanished climates, vanished continents, and vanished forms of life. Nothing in that motion requires the past to remain, yet traces of it endure in stone. The fossils never tell us what the ocean intended. They only preserve the results of countless generations adapting to conditions that no longer exist. A jaw, a tooth, a vertebra, or the outline of a buried body is a small surviving fragment, yet together, these fragments reveal a recurring tendency. When marine ecosystems have enough time, life repeatedly explores the outer boundaries of size, speed, strength, and specialization. That pattern does not mean evolution moves toward perfection. There is no destination waiting at the end of a lineage, and no invisible ladder leading from smaller animals toward larger ones. Most species remain within familiar limits, shaped by the immediate demands of finding food, avoiding predators, reproducing, and surviving changes in their surroundings. Extreme forms appear when particular combinations of energy, habitat, prey, anatomy, and time happen to make them possible. The prehistoric ocean became a place where those combinations repeatedly occurred. Large bodies could be supported by buoyancy. Food webs could sustain enormous hunters. Open water provided room for pursuit, ambush, migration, and escape. Across different geological periods, entirely unrelated animals found their own ways to occupy the same broad ecological position. Their bodies differed profoundly, yet the pressures acting upon them produced recurring solutions to the same basic problem of capturing enough energy to remain at the top. What makes the fossil record especially meaningful is that none of these animals was designed with knowledge of the others. Dunkleosteus could not anticipate the ichthyosaurs. Pliosaurs could not know that mosasaurs would eventually dominate the Cretaceous seas. Each lineage responded only to the world immediately surrounding it, while the deeper pattern became visible much later, through the accumulation of fossils and geological evidence. Some of those fragments have waited for extraordinary lengths of time. A jaw discovered on the coast of Somerset belonged to an animal that lived during the Triassic, roughly 202 million years ago. The specimen remained hidden within rock until erosion exposed part of it to a child walking along the shore. Its discovery was not the result of the animal being preserved for humanity. It was simply a meeting between ancient geology and a modern moment. In Arctic rocks, remains of enormous Jurassic marine predators have survived through the movement of continents, repeated changes in climate, and the gradual reshaping of landscapes. Their bones became part of the sedimentary record, while the animals themselves passed entirely beyond the reach of memory. Elsewhere, teeth and fragments continue emerging from exposed beds as rain and erosion remove another thin layer of stone. There is something fitting in that process. The ocean built its creatures according to circumstances that lasted for millions of years, while the record of those creatures returns to us according to the much slower rhythm of geology. A fossil does not arrive because the world is ready for its story. It appears when erosion, chance, location, preservation, and human attention happen to meet. That is why the record can never be treated as complete. Every discovery changes the boundary of what can be known, while countless animals remain beyond recovery because their bodies dissolved, were destroyed, scattered, or were buried where no future erosion will expose them. The creatures we know are therefore not a final inventory of the ocean's giants. They are the surviving pieces of a much larger history. And perhaps that is the gentlest meaning hidden within all these vanished dynasties. Life does not preserve its achievements, it simply continues, generation after generation, adapting to whatever world remains. Sometimes that continuation produces a fish with crushing jaws, a reptile longer than a city bus, or a predator whose anatomy seems almost impossible until the fossils place it before us. The rock gives back what time allowed it to keep, slowly and without urgency, while the ocean continues making new histories that will one day become ancient. The ocean has outlived every dynasty described here. Its waters have crossed coastlines that no longer exist, filled basins that later became mountains, and carried life through changes so extensive that entire families disappeared. Yet the sea itself remained, offering new generations the same fundamental elements of existence: energy, space, prey, competition, and time. Nothing living today is a direct continuation of the great predators that once occupied the highest levels of these ancient food webs. Their particular bodies are gone, their hunting strategies broken by extinction, their bones scattered through sediments that have since hardened into stone. Yet, extinction does not erase every consequence of a lineage. The pressures those animals imposed became part of the environments in which other organisms evolved, and surviving species inherited bodies shaped by a world that included predators we will never see. A sea turtle carries a shell whose architecture reflects many pressures at once, including the need to balance protection, movement, and the cost of carrying armor through water. Open ocean fish gather into schools, creating confusion for predators, while allowing many individuals to respond to movement almost as one. Deep diving whales possess physiology that allows them to descend into regions where pressure becomes immense. Oxygen is carefully conserved, and sunlight disappears. None of these traits can be assigned to one extinct hunter, yet each belongs to an ocean whose history has always included pursuit and escape. The physical evidence remains scattered across the world. White cliffs in England preserve the accumulated remains of microscopic marine organisms. Prairie landscapes in central North America expose sediments deposited beneath an ancient inland sea. Arctic rock preserves fragments of Jurassic ecosystems beneath frozen ground. Along the coast of Somerset, erosion continues to expose pieces of a vanished world, just as weather and flowing water reveal fossils from older rocks elsewhere. Beyond these familiar places lies a far larger archive. Much of the seafloor is covered by sediment that has never been examined in detail. Beneath it are layers recording ancient climates, volcanic eruptions, changing shorelines, shifting currents, and communities that may have left behind organisms unlike anything yet known. Deep ocean basins are difficult to reach, and the geological record is uneven. So many chapters of marine history remain hidden simply because the right rocks have never been exposed. Even the oldest part of the story extends far beyond the predators considered here. Life has occupied the oceans for more than 3 billion years, long before vertebrates developed the jaws and bodies that later became dominant hunters. During that immense interval, evolution repeatedly found new ways to capture energy, endure changing conditions, and exploit newly available habitats. The forms changed, the underlying process continued. Today, the ocean covers roughly 71% of Earth's surface and reaches an average depth of about 3,688 meters, roughly 12,100 feet. Vast regions remain difficult to observe directly, particularly beneath deep water and within sediments. What seems familiar from a coastline or a research vessel represents only a small portion of the environments available to marine life. Somewhere within those unseen places, Organisms are already responding to the conditions of their own age. They are not preparing to become monsters, and evolution has no plan waiting at the end of the process. They are simply surviving, reproducing, competing, and changing as generations pass. Given enough time, some of those changes will become fossils, while others will disappear without leaving a trace. Millions of years from now, the sea will still move beneath a different sky. The creatures of this age will belong to the deep past, their remains altered by pressure, sediment, chemistry, and stone. Somewhere, perhaps in a cliff or beneath a future seabed, a fragment of their existence will remain, waiting for a world that does not yet exist to uncover it.